Hey everyone! In the next two lectures, we're going to concentrate on one of the most powerful, yet misunderstood concepts of functional programming, and it regards the usage of type parameters for data types and functions. But let's start by reviewing the list data structure. In Scala, a list is a linked list, meaning that every piece of data is connected via a single link to another list. And at the end of all lists, there is this unique construct called nil, which represents the empty list. But for now, the most important point to remember is that list is generic. For instance, you see the square brackets after the name of each list. This indicates that we can put any type of data inside it. We can have a list of int, a list of string, or a list of users. And it doesn't matter. And that makes sense. Because when we create a new type, we wouldn't want to create a new data structure from scratch just to store it. Now that we have a generic data structure, we also want to avoid duplication when we implement standard methods like size. After all, computing the size of a list is independent from the type of the element that it contains. So the question is, how can we avoid repeating ourselves? We make the function itself generic by adding a type parameter to it. This is like a type variable. Here I call it a, which is a fairly common choice when we have a single type parameter. But we could call it anything we want, like lm for example. But one thing to note is when we call size, we don't have to specify the type parameter. For example, we don't need to say that a is an int or a user. The compiler can generally infer it from the context. And this process is called type inference. So now, what about a more complex function, like map? Map is also parametric. It takes a list of A and an update function that will apply on every element. As you can see, we can map, for instance, a list of int or a list of string, and it works perfectly well for both. But the problem with this signature is that we can't change the element type in the input list. For example, if we have a list of users, we cannot use map to get their names. If we try to do so, we'll get a compile time error, and we can see it here. It says type mismatch. Now, the rest of the error message is quite confusing. The compiler tells us that it found a function from user to string, which is correct, that's what we passed. But it expected a function from serializable to serializable. Where does this serializable come from? It's related to type inference. The compiler tried to guess A and somehow got confused. When you are in a similar situation, there is a simple trick to help the compiler. We can manually annotate the type parameter of map. Here we can say that we expect A to be user, which leads to a much more informative error message. Now the compiler tells us that in the specific section of map, it expected a user, but it got a string, which is precisely the issue that we are facing. So how can we fix it? We add a second type parameter to map. Often libraries call these two type parameters A and B, but it's not mandatory. We can give them a much more meaningful name, like from and to. From will be the element type in the input list, and to the element type in the output list, which makes update a function from to. And now with this definition, we can extract a list of names from a list of users. And we can still increment a list of numbers as we did before. This means that from and to may very well be the same type. Just because we define two type variables doesn't mean that they cannot be assigned to the same value. Now there is still one annoying thing about this example. Can you guess what it is? It is the definition of the anonymous function. It's a bit tedious to annotate the input type, especially when the code is so short, as it is here. Ideally, we would write user arrow user.name, or even underscore.name, using the placeholder syntax we discussed in the exercises. However, if we try that, we would get a compile time error that says missing parameter type, meaning that the type annotation must be mandatory. which is weird if you think about it, because the compiler knows that map takes a function from to to, where from is the element type of the input list. And in this case, we have a list of users. So the compiler should be able to infer that the update function takes a user, right? Yes, it should, but in Ch02, the current major version of Scala, the compiler cannot use type information acquired from one argument to infer the type of another argument in the same parentheses. This means that here, even though the compiler knows that from is equal to user after analyzing the first input, it cannot use that information when it infers a type of update. This is unfortunate, but there is a workaround. If we refactor map to have two parameter groups, meaning that its inputs are split into two sets of parentheses, then the Scala compiler can infer the type of the update function without any issue, because the inference is done one set of parentheses at a time. So this is a pattern you will see in almost all Scala API out there. If a generic method takes a function, we generally put it in a different set of parentheses at the end, so that the compiler can easily infer its type. By the way, in Ch03 or Dotty, we'll not need this trick anymore. Generally speaking, the type inference in Ch03 is miles ahead of Ch02. And many limitations like this one have been removed. That's definitely one of the reasons why I'm so excited about Ch03, because the language is going to be so much simpler. Okay, so far we have only talked about generic types that are data structures, like list. But parametric types are not limited to data structures. There is more to them than that. And we'll practice working with more varied kinds of generic types in the exercises. For example, we look at JSON decoder, which is an interface that lets us transform a JSON document into an arbitrary type. And we can have a JSON decoder for int, string, or list. And we'll implement a few generic functions to combine and manipulate this interface. We'll also practice with predicate, a wrapper for a function from A to Boolean. You know, the kind of function we use for filtering. And we'll implement powerful combinators like AND, OR, negation, and much more. So to summarize, we have seen the most obvious benefit of parametric functions. The fact that we can drastically reduce code duplication by having a single function that applies to many types. In the next video, we'll cover another advantage of generic functions that is even more powerful, yet often misused. So stay tuned.